Hi, I'm Dr. M. Kamakshaya, open source software evangelist and also a full stack web developer. For the past few videos I've been explaining about how to perform few statistical tools. Few statistical tests for both I'm talking about both parametric and non-parametric statistical test. I explained T-Test and also I briefly talk about few non-parametric tests. In this video I'm going to show you how to perform Anova. Anova is actually the darling of statisticians. The full form stands for analysis of variance, and in case if you want to study what is Anova, you just have to go to Wikipedia. You don't need to study. I don't suggest you to have any. If you are interested, you can also refer textbooks, but I think for me this is here you can pick up Anova. The very first statement can let you know what it is. Analysis of variance is a collection of statistical models and their associated estimation procedures, such as the variation among and between. We have like within and between tests inside Anova. Analysis of variance used to analyze the difference among group means in a sample. So this Anova helps us to assess the differences between the group means. That is why the null hypothesis is usually mu1 is equal to mu2 is equal to mu3 is equal to something like that. And the alternative hypothesis always is going to be at least one mean is different from the rest of the means among these groups. So there is a history, there are examples here, and background terminology, something like that. This is not very much of course here design of experiments is one very interesting area of operations where Anova is used. This Anova is used in almost all areas of domains of knowledge for different there are kinds of models like fixed effects model, random effects models, and mixed effects models. These are all a bit advanced and I'm not going to talk about all those things here. There are, I think this is actually the methodology when it is mentioned as logic. The principal tenet or the objective function in Anova is the sum of the squares, and how we are going to calculate the sum of the squares. The sum of the squares total sum of squares is equal to error sum of the squares and treatment based sum of squares. This is SS error, SS treatments. The treatment means actually the amount of variance explained by the independent variable in dependent variable, which means we have two parts in Anova formula, the LHS and RHS. So how much of the variance in LHS is being explained by the variables that are in RHS is what is called the treatment. And this treatment is what is the interest of the topic, and error anyway this is the total is equal to treatment, the truth plus error, something like that in very brief words. And we try to assess the evaluate the effectiveness of the Anova based on a test called F-test, and this is how the F-test is being calculated in Anova. F is equal to variance between treatments by the variance within treatments. Suppose you imagine you have some groups like group 1, group 2, group 3, group 4, something like that, like a cost tab or maybe a contingency table. Each cell will be a group, and now each group will be having a mean, right? And all these means can be explained with the help of a grand mean, which is an abstract mean for the entire the sample. And now the between treatments is the difference between each mean to the grand mean, and within treatments is the difference between each element to the grand mean. That is, now the between is called the treatment and within is called the error. So whenever we encounter between effect, something like that, we are trying to assess the effect of the treatment, means the difference between the means. Whenever we speak about the within treatments, we are trying to talk about the error attributed to the entire fitness, which means the difference between each element to that of the grand mean kind of thing. So this is the brief and this ratio yields F statistic, and we'll be interpreting this F statistic based on the p-value that we get automatically in R. We don't need to worry about we don't even need to look at the F statistic, as far as not only in R, for that matter SAS, SPSS, whatever the tool uses, the p-value will be calculated automatically, and we just have to interpret the p-value to take the decision or inference. Decision means usually we call inference in statistics. In other words, it is called decision. Okay, that is brief about Anova. And now suppose we need to add action to this theory, and will be using R and RStudio for this analysis. Suppose you want to study something about Anova, like how to perform, because let me mention that I don't know anything about Anova. Now what I do, how to perform Anova in R, something like that. You can just go to the browser. Today you don't need to refer any textbook, you have quite a few. I will suggest you one very interesting portal, that is QuickR. So here you have very brief about, for that matter you can just come straight away to QuickR to refer to any kind of, you have this left side, you have all the sections like descriptive statistics, frequencies, crosstabs, correlations, T, and everything. This is sufficient for you. So by the time you reach to the end of, you'll be done with MF. Now whenever we're performing the Anova in R, we call it as a fit. Now this is what is the protocol to perform analysis of variance inside R. The LHS, left hand side will be having an object. This is user created object. We simply call it as fit. And this is the left assignment operator in R, and you have a function called AOV, this analysis of variance, something like that. And here this portion of this statement is called the formula, and a couple of minutes ago I was referring to LHS and RHS. This is what is called LHS, this is RHS. This is just a regression formula. We are yet to take the topic of regression. I did not enter into regression, but from here onwards we will be following the same protocol until regression. The group differences starts with Anova, even for that matter from T-Test, very simple T-Test, and that will continue till the end of regression. So the principal difference between the T-Test and Anova is that T-Test most of the time we use, both LHS and RHS will be the continuous variable, which means some numerical data. But whenever you, every time we will not be having continuous data either side of the formula. Sometimes we have factors, mostly like this left hand side will have continuous variable, which means numerical but non-categorical, and right side you will be having some grouped data like interval data. This is something ratio versus ratio or interval by ordinal, interval by nominal, something like that. Suppose if you are interested to, I will be talking about data in few seconds. So this is called formula, and you have LHS and RHS. In LHS you have continuous data, and RHS you have categorical data. So each category is a group kind of thing. Now we need to tell R where our data set is. So this is the entire statement to execute the AOV. Now this is one way AOV, which means one way Anova. You have only one factor. Suppose if you have two factors, then you have it is we don't call two-way Anova, it is still one-way Anova, but whenever we bring in some interaction between these two factors, yes, here you have the formula. So like this, you have LHS you have a continuous variable, and RHS you have two factors, and we are interested not only on the effect of each factor over the continuous variable LHS, dependent variable. By the way, we call this dependent variable. These are, I mean, we are ready to take up the discussion about what is dependent, what is independent kind of thing. But in other words, you can also imagine, you can I mean, make a little intuition by imagining that LHS is dependent, RH is independent, something like that. Whenever you are interested in some interaction, suppose if you assume that the interaction between these two factors also influence this dependent variable or LHS continuous variable, then that turns out to be two-way factorial design, something like that. Just because you have two factors, you cannot imagine that it is a two-way factorial design, two-way ANOVA. You should explicitly, and one way or the other way, you should be interested. I mean, whenever you wanted to assume some interest in interaction, then we can talk about two-way. I mean, that turns out to be two-way ANOVA, something like that. Now, there is another thing called ANCOVA, analysis of covariance. This is a special case of the ANOVA. And here in the formula LHS, you have a continuous variable, which means the ratio or interval. And right hand side RHS, you have a factor and a continuous variable. So one ordinal or nominal and one ratio or interval data. So till here we have LHS, we have ratio or interval based data, and RHS you have nominal or ordinal data. But here you have in ANCOVA, suppose if you want to mix some ratio or interval data together with a factor, then you can assume that technique is referred to analysis of covariance. Now this is within effect, one within factor, something like that. That is a special case. I don't like to complicate my demonstration. I have to go in a lengthy way to talk about this. It will consume some amount of time. Then this will take up. I'll try to discuss about this within and between effects, possibly in another video. Now there is an interesting aspect in R, that is R is very much powerful as far as plots are concerned. You can create wonderful eye-catching visuals. We can also plot graphs whenever we perform some analysis of variance, and the very simple way of obtaining the visuals is using a method called plot. So I'll be telling you, but please be cautious, you need to use the fit. So this fit has information related to analysis of variance. So this is we call the fit is actually an object created as a matter of performing analysis in R. This is an output. In simple words, we have the output, all output information inside this object fit. That information should be supplied to this function plot. Then we'll be able to see how many plots we have. 2 by 2. I think 4 plots. That's too much. I mean, that is sufficient to have, not too much, but and then there are model evaluation effects. We can, there is a concept called type 1 error and type 3 error. You can call, I mean, SS is actually the shortcut name for sum of squares is error. There is type 1, type 2, type 3 types of, that is an advanced topic, and I don't like to spend more time talking. Maybe perhaps I can come up with one more demonstration exclusively dedicated to this type 1, type 2, type 3 kinds of usually now whenever you perform ANOVA, it is type 1 error, unlike in SPSS, it is by default you have type 3 error. In type 1 error is the best thing because it has almost all effects covered inside that method. Personally I don't like type 3 error, which is the default method in SPSS. That is actually the biased. I mean, you are in favor of a particular situation, but type 1 always yields the total situation. You are not in favor of any particular hypothesis. All the hypotheses will be covered in type 1 error. So I mean, it is a total wholesome analysis kind of thing. So it is always better to go for the type 1 instead of type 3. Anyway, I'll take up this discussion in future in one of my videos. Okay, you have a particular thing called multiple comparisons. Usually we use Tukey's honestly significant difference. We have THSD kind of. You see here THSD, HSD. You can also go Tukey's difference. We refer this to Tukey's difference. Tukey, HSD, and fit will give you the group by group differences. And why do we need that? There is a simple reason. Sometimes we are interested in analyzing the group wise differences as which difference is significant, which difference is not significant, kind of thing. So if that is the interest of your analysis, anyway I'm not covering that, but we'll see. Okay, and there is another advanced method to cover ANOVA, to obtain the visuals related to ANOVA. There is a function called interaction plot. You don't need to install any package. You can just this is available from the base this is R-base function. You can just straight away use this function to obtain the interactions. You can add visualization to the interactions. And then you also have gplots library. You need to install this package if you have sufficient infrastructure with you, if your workplace allows you to install the packages. You can just install this package and just go ahead. And there is another thing called MANOVA. This is a multivariate analysis of variance, and there is another thing called MANCOVA, multivariate analysis covariance, multivariate analysis of covariance. So it is same, like as much as the difference between ANOVA and ANCOVA. But in MANOVA, what happens that you have multiple variables in both sides, LHS and RHS. In ANOVA you have one single variable in LHS. In MANOVA you have multiple variables in LHS and multiple variables, more than two variables in RHS, in both LHS and RHS. In MANOVA there is a methodology. It is not like interpreting the results straight away with the help of F statistic. You need to study MANOVA Wikipedia. There are a few statistics to obtain. We interpret that with the help of few statistics. You see here we have Wilks, lambda, Bartlett's, Pillai. We call KCC and Pillai MS Bartlett trace. This is actually there is a measure called the hypothesis depends upon an objective function. A is equal to sigma model divided by sigma residuals, kind of thing, and you have to go through this methodology for MANOVA. That is a very, very interesting topic. You can come here and read about we obtain this statistic. Based on this statistic we interpret the results in MANOVA. Here you can choose the test. This is called Pillai test, which means this statistic. Here you have the Pillai, lambda Pillai. This is the objective function for that, and here the software will try to optimize the data for to evaluate this function, and it will yields a particular statistic, and this is the function to perform the MANOVA. But anyway, we are not going to do this because I am not going to talk about factorial designs. You have a factor in LHS and a factor in RHS. Then only in RHS especially you have group data, either it is interval or ordinal or the nominal kind of thing. Okay, now this is all about introduction to ANOVA, and now let us jump into the action. I have RStudio. Just now I installed this very latest RStudio. I think it is better to try this here, so that by the way, I am using Ubuntu 18.04. In my previous demonstrations I used Windows. It doesn't matter. Okay, as far as you just have to ensure that you have R and RStudio installed properly in your computer. Okay, let me put it here. Yeah. I already started RStudio. I don't know why it is. Yeah, it started, I guess. Yes, this is how your RStudio looks like the very first time when you see I installed the very latest R version 3.6.3. If you want to check, let me close all these tabs. Yeah. Now or latest version, you can just straight away, you don't need to worry about 3.6.3, right? You can just go here. I think you will go to the rproject.org 3.6.3, and now let's see here 3.6.6. so the latest, holding the windsock, that is the name of the R language. Now RStudio, you can check here. We'll check for about RStudio. I think I have the latest version 1.2.5033, something like that. I don't know the number, but this is the latest version, just a couple of minutes before I install this RStudio. By the way, I'm using Ubuntu 18.04 LTS version. It is Linux. Because I am open source software evangelist, I always prefer to use open source software for my data analytics and science needs of my teaching and training, and also industrial consultancy. You can use Windows. Suppose if you are in Windows, the procedure is same. You are not going to use different tools in Windows. The same RStudio and R programming language. You just have to install from the same portal. Say from here. So you have to download from. This is for Windows. You just have to download and install. That is very core fundamentals. And then let me straight away go to the topic now. Now let me take up the data sets. Now where are you going to use this Anova? So you can use Anova. Since I'm a business analyst, most of the time I talk about business data sets. Now you see you have different functions in business. You see here in down, this is actually the LibreOffice Calc. In Windows you will be having Microsoft MS Excel, and this is a spreadsheet application, default spreadsheet, not default actually, this is a spreadsheet application in Linux. You have the same kind of you see here the left bottom corner you have the tabs. These are the sheets. This is a workbook. In marketing you come here, like I just organized the data. I have three variables here. You see the sales performance depends on salesman incentives and advertisement expenditure. Obviously any concern, this is the model in my, I need to do analysis on these variables, and you can choose any other variables, but see that you have this sales performance is going to be the variable in LHS, and the salesman incentives and advertisement expenditure will be there. Now the problem is, I said, or we read that the RHS we need to have the factors. You say here these are not the factors. Factor means any variable which has levels. That is what is called the factor. Either you can convert this. This is actually the ratio data. This incentives is measured in terms of currency. It can be 11 lakhs, 88 lakhs, something like that. See here performance is 10. Sales performance may be 10 crores, and this 10 crores achieved the assumption. So we are assuming that the performance depends on incentives and advertisement expenses, which means promotional, the money which is spent on promotional activities by the firm. Now you see this is 11 lakhs and 49 lakhs, something like that. This is crores. This is just a demonstration. Don't be so serious. Now if you say 11 lakhs, 11.5 is also valid. So this is actually ratio data. Continuous data, non-categorical, and this is continuous non-categorical, which means ratio or interval. Now how are you going to change this? So you somehow have to find, if in spreadsheet application, just you can do the same thing even in. Now I'm just telling you that you cannot have the continuous data. If you have the continuous data, you are going to bog down. Your analysis will not be reliable. So this is 11, right? So knowingly that this is 11, anything greater than 10, come on. This is, if this is less than 20, then write it as 0 to 20, else B2, keep the B2, something like this. Now you see 0 to, like this we need to convert the entire. This is how you convert that into. Now you can come back here and take it off. I'm just telling you how to convert the continuous data into categorical data, because you need to. Now this is a fact, this is a level, this is not a number. 0 to 20 is not a level, it has no numeric value, it is just a string, character based data. So this is how you can make the superior data into the inferior data by simply converting that, making into categories, converting that into categorical data, something like same activity you had to do for. Generally it is possible for you to go for the Anova. You cannot straight away employ this because we cannot get this type of data from the field. Do you follow what I am talking? So either you have categorical, if you have categorical data you can just straight away go for the analysis. If you don't have the categorical data, then you need to, I'm just talking to the people who are interested in the projects. Like you may be having data right now in your hand, so every time you will not be having the categorical data. If you have it is good, but no, it is always better to have non-categorical continuous ratio based data instead of categorical data, because this is inferior data. It is always better to have, you see now I converted this non-categorical into categories, but if I have the categories it is difficult to convert into the non-categorical data. So it is always better to have the non-categorical data. At any moment in time we can just convert that into the categories. So that is what, this is an example for the marketing, is a marketing example in business analytics. Now let us go to the finance. Here I have stock market returns, and that depends on the previous day returns and profitability of the firm. That is one simple situation. You can have any type of variables. I have this situation in my hand, and again I simulated. You see here I have a function. These are all fake data. I just simulated all these data sets for the sake of examples, not real-time data. You can have real data in your hand, but the situation is same. So you can make some postulations or assumptions or a hypothesis that stock market price, returns depends on the previous day returns and profitability. If that is the given, again once again this is very strictly numerical, continuous, ratio based data. You see decimal value is valid here. There is a float point in this value. You need to convert this data into categories well before you go to the. We have here again some numerical data, and here this is for HRM. So in HRM you can make some postulation between employee performance depends on, maybe the firm's performance depends on employee engagement, and you see here actually these are again fictitious ratios. This is engagement. 33% of the employees are engaged 33% of the effective 33% of the total time effectively in the process, and employee performance is indifferent. This is actually the scale data. It's numerical, it is ordinal data, and now this is the ratio. You see again this is actually the reverse case. You need to convert this into the categories. Okay, maybe 0 to 0, 10%, say 10% to 20%, 20% to something like that. So now here the assumption is employee performance depends on the employee engagement and training expenses, something like that. How money is spent on the training and the ratio of engagement, and that gives rise to pick up here. This is the file, and the employee performance is high, where engagement is only 18%, and training, the amount of money spent on 95% of the budgeted money spent on the training, something like that. Now let's go to the operations. Here maybe you can assume a situation where the quality depends on the intrinsic value of the material and the process design. And every plant you have some design of manufacturing, service process or maybe production process. You have a design, and the design, this is actually the scale. You have unfair, fair kind of thing. You have intrinsic value, again this is very high, not so high, something like that. And quality, again you have very superior quality, intermediate, not so superior kind of. These are all scales. This is categorical, you don't need to worry about, so you can straight away go to the analysis. Here you have this is a group data, and again this is also group data. This is not continuous. You can maybe the best scenario could be you can assess the quality in terms of ratio, so that maybe 30% quality, 40%. Okay, let us use that kind of No, this is just a demonstration. Please be cautious. I am just cooking up all data, so you don't need to. I'll just come up with yeah. Now this makes some sense. We'll take up this data set and I'll just copy so that case special to numbers. Now this makes good. Now we need to. Now the assumption is going to be the quality depends on. This makes a bit. We have left side LHS. We have perfectly continuous data, and here RHS we have the categorical data, which means group of data, so that we can just this is operational operations. Now how to take this data into R. Okay, I am going to tell you as usual. We are going to save this data as in the form of CSV file, because or is you can just take a ODF file also as it is inside. I prefer to convert that into CSV file, and this is going to be operational data. Okay, and I am in this folder. You need to say active sheet was saved. Now we'll go for the entire sheet. I think we have that sheet. This operation CSV Anova, ODS. We have both of the files, so I'm just afraid that I may lose this. Now we have CSV file. Let us go back. Let's start. Now this is the active content of my demonstration. I call quality data qual dat, dat, and then read CSV file choose. So if you don't know what it is, please refer to my previous demonstrations. So you just have to press enter, then you have to take up the data set. I saved it in some directory. I'm just going back to data. Now I have operations CSV. Okay, now I have qual dat. Yes, I have the data inside R now, and now names have qual dat. Oh, you got quality and intrinsic value, process design, something like that. Now as you remember, we have a formula Anova. Suppose you don't know what is Anova, help. I told you that there is a function called AOV. As I was mimicking, I don't know anything about. Now you got the very brief documentation to your analysis of variance, fit and analysis of variance model, something like this. Is the syntax for. You have the formula, you have the data, and these are all actually, you don't need to worry about all of them. Now you will get some values. I think values are okay. We can use summary to get all. Now you have an example here. You can just follow, copy paste all these things and learn how to perform AOV and analysis of variance inside RStudio. But I am just going to take a very blunt approach, brute force approach, like I don't know anything about. Now I call fit and then AOV, then I need to mention this, so it is better to names of quality dat, right? Quality. Now fit left assignment operator AOV, and then you have quality depends on factors, intrinsic value, and then plus process design, and then where is the data? Data is in qual dat. Now press enter. If everything is okay, then R becomes silent, otherwise it return error message. We don't have any error message. Now this is the fit. Let us understand the fit. This is the statement which we executed to perform analysis of variance over our data sets. Now we have the terms sum of squares, degrees of freedom. Do you remember in your +2, or maybe in your, if you had a little bit of exposure towards statistics in your previous we have an Anova table. we just call it as an Anova table. You have sum of squares. This is called SS. By the way, this is type 1 SS. I don't want to make my demonstration controversial. You can spend time and read what are type 1, type 2, type 3, type 4 sum of squares, but mostly whenever we perform ANOVA, our returns type 1, which is best scenario. Now for intrinsic value, this is sum of squares. This is actually the error, and degrees of freedom, this is the process design and degrees of freedom, and then you have residuals, and then degrees. This is the SS attributed to intrinsic value, SS attributed to this, and SS attributed to residuals. If you remember our ANOVA introduction, we have a particular formula called SS total is equal to SS treatment plus SS error. So this is SS treatment and this is error. SS treatment for design, process design, and error, something like that. Now you have the residual standard error. This is the residual standard error. It is 0.31, which is less than 0.5. There is no benchmark like that, but I don't think we have such a big error in our, but sometimes the 0.3 is also a big error in some situations, but in our situation we need to go further in order to assess whether this is a big error or small error, something like that. But anyway, this is not the right way to interpret the ANOVA. We have another method called summary. If you want to get the entire output for this analysis, it is better to use I think fit. You see, this is actually the ANOVA table. This is not the ANOVA table actually. This is it only reveals you the sum of squares, which we read while through Wikipedia when I was explaining what is another variance. That is SS total, SS treatment, SS error, something like that. This is SS treatment, this is SS error, and this just about the sum of squares. And now this is the ANOVA table. You see here you have variables, intrinsic value and process design. Now degrees of freedom 1, 1, and then sum of squares is this same value 0.0799 and 0.11, and then you have the residual error for 12 degrees of freedom. You have 1.1813, and then mean sum of squares, which is this value divided by 12. You can also cross check that. Let me do that for 0. This value. Let me take up this value. Okay, and let me copy that here. I don't need to divide it by 1 because this is always going. That is why you got 0.07. Now let us take this value. I was correct in my first attempt, but I changed. Now let us divide it by 12. Okay, and see what's going to happen. That is going to yield this value, mean sum of squares. Now this divided by this, this is this value, this divided by this is this value, and now this divided by this is what is this p-value. Okay, no, I'm sorry, not this divided by this. This is the p-value for this f value, this is the p-value for this f value. And there are procedures in R. You can also compute, check back. Anyway, I need to spend a little more time to compute this p-value for. I'm not interested in that, but you can figure out how to get this p-value for this f value. Maybe I can make some other session which I can talk about how to get the. You got a function called pf. Okay, you can give any value here, like 0.5 for some degrees of freedom. Maybe some 10, then you will get 2 degrees of freedom. There are degrees of freedom 1, degrees of freedom 2. Let's give 5, and then you will get a p-value like this. So in this way we try to do. Maybe I can I do this for point. There is nothing wrong. We can always try, make an attempt. And then degrees of freedom 1, degrees of freedom 2, 12. Now let's see, 0.61. Okay, now let's change 12 and 1. Now 0.28. Yeah, this is neither 38 and neither 0.8 f value, and degrees of freedom 1, degrees of freedom 12. So that's actually, we need to do a little bit of process. Actually, this is not the way we come. Anyway, this is the p-value for this f value, this is the p-value for this f value, this is the f value for intrinsic value, this is the f value for. Now what all these f value and p-value? As I said, don't look at the f value, just straight away go to the p-value, and if you see the p-value, this value is greater than 0.05, which means 0.05 is a threshold value. In all circumstances we use this 5% significance level. So this value is greater than 0.05, so we straight away can come to a decision that we are not able to reject the null hypothesis, that the mean values, the difference between the mean values of these variables, these three variables, it is not statistically different, I mean significant. The differences between the mean values of these three values are the variables, or the study variables. The differences between the mean values of these study variables is not statistically significant. That is what is the null hypothesis. So this is something going to be mu1 is equal to mu2 is equal to mu3, something like this. So this is actually the null hypothesis. Your null hypothesis is going to be like this, and your alternative hypothesis, at least one mean is different from the rest of the means, or you can say mu1 is not equal to mu2 is not equal to mu3, something like that. So here if you look at this p-value, the mean value of this variable and mean value of this quality to that of quality, we are just comparing the mean value of intrinsic value to quality, and now the difference between these two mean values is not statistically significant. So both of them are, so don't ask me the question like, what are the mean values, and you can do that. You can just simply use the mean function, and there may be different, but it is always different, but that different, is it statistically significant? That is what is the question. So that difference is not statistically significant, means there may be difference in the sample, but that difference in population is not worthy for consideration. That is what is the meaning of this analysis. Now we have this second variable, the mean value of process design is not statistically different from the mean value of the quality, and now you see here the p-value is far high compared to 0.05, so at 5% significance level we fail to reject the null hypothesis. So the null hypothesis, given the null hypothesis is like this, so the difference between these two variables is not statistically significant. So the overall the decision that the quality pretty much depends on these two variables. The quality in this particular form pretty much depends on the intrinsic value of the material and process design, the sophistication of the process design. So there are very good relationships. All these three variables are interdependent, and the quality is pretty much influenced by these two variables in this situation, in this data. Okay. So we can assume the relationship is a valid relationship, and we can use this relationship for the further decisions. This is how we can perform the analysis of variance inside using the R programming language inside RStudio. RStudio is just an editor. Hopefully I will come back with some other statistical technique in my next video. This is for this video. Thanks for watching this video. Stay tuned to the new content. Please press like button. Please kindly press like button. If you either you liked it or not doesn't matter, but please press the like button and stay tuned to the new content, and also subscribe to my video channel. Thanks a lot.